Just the one.
What size resistor?
We're going to talk about that. Yeah, so here's what our test circuit's going to look like. And we're going to be putting this onto our MyDAC, and we're going to be able to plot out our characteristics curve for our diode. So this is called when we hook it up with what it's called is it's going to be called a two-wire characteristics curve, meaning that we're doing so we can do any two-wire component. So we can do a resistor or a diode, an LED, anything that has two leads on there, and we can see what the characteristics curve would be in relationship between the voltage and the current. So it's another name for them, our VI characteristics curve. And the one that we're going to be using is going to be looking at the two-wire VI curve. So here's what our test sample is going to be. We're going to have our variable power supply, and we're going to be, in our first operation, we're going to do it as a forward biasing. So we're going to be varying our voltage from 0 to 10 volts. Then, on our MyDAC, we're going to be sensing through the wires. So this one here is going to be coming out of our analog output, and that's going to be our 0 to 10 volts. And then going into our MyDAC, we're going to sense the voltage, and this is going to be our AI. Make sure I'm going to go do it the same way the documentation is. If you download those files, I do have the link for it for I don't know, the setup of it. So what we're going to do is we're going to be sensing the voltage across the diode, and we're going to be sensing that voltage using our analog inputs, using what we call the differential mode. So it's going to be our AI plus 0 is going to go here, and then the other reference point is going to be our AI minus 0. So all we're doing is we're just going to go into our analog input. We're going to compare the difference between the analog plus 0 and the analog minus 0. And that's going to sense our voltage going across that diode. And this will give us our voltage across our diode. So that's going to be our voltage. That's going to be our analog input channel 0. That's going to be our x-axis. Then our other axis that we're looking for, that's going to be our current. And so then we have to measure our current. Well, our analog inputs, all they can do is they're looking at a potential difference between our voltage. So we don't have a way of actually having a current input. So what we do is we use a resistor. And this resistor is going to be our sense resistor. And this is going to be used for our current of our diode. Since all we have is a series circuit, and we know that our current is going to remain constant, so whatever the current going through the resistor is going to be the current going through the diode. So we're going to just sense the voltage. So what we're going to do is we're going to put on some couple of sense wires on here, and we're going to sense that voltage going across that resistor. And so this is going to be your analog input plus 1, and then we're going to be on the more negative side of this resistor. And this is going to be your analog input minus 1. And that's going to sense the voltage across that resistor. And then now for the MIDAC, in order to calculate out the current going through that resistor, then what we're going to do is we're going to tell the MIDAC that we're going to just use, and for this test purpose, we're going to just use it as 10 ohm. That's the one that's called out on the website here, and I'll show you that website here. So once we know that we have a 10 ohm resistor, and once MIDAC knows that what the voltage is, then we can go ahead and calculate out that current going across that resistor. So we're just going to take our voltage of our resistor divided by our resistor, and that's going to give us our current of the resistor. And once we know what the current of the resistor is, then that's going to equal our current of our diode. And so then we can go ahead and we can get our y-axis off of the channel 1. So then what the MIDAC is going to do then is now we got everything all set up. This is my analog output. Channel 0, and then our A ground. Okay, but I just have it simulated as a variable power supply. Now when we always talk about our analog output, channel 0 or channel 1, remember that we're looking at it as coming out of that op amp. Always, there's some confusion in AC there, where we wanted to just bring that wire going into either our RC circuit or our RL circuit, and we went right to the analog output. If we call out the analog output, make sure that you're coming out of that op amp, the one that we wired up in there from day 1 there. So just start using that analog output. If we call for the analog output, either channel 0 or channel 1, make sure that you're coming out of the op amp. That gives us enough current to power up any of our circuits. Otherwise, if we just come out of the analog output directly from the MIDAC, there isn't enough current. We only have about 2 milliamps of current capable for us. So the other way we have 20 milliamps. Okay, so what the MIDAC is going to do then is it's going to just start to go and do certain increments depending on how many steps we tell it to do. So we'll just use for an example here. We're just going to set it up as a 0.1 volt sample. So what the MIDAC is it's going to go ahead and it's going to take a look at. It's going to put 0 volts in there for our voltage. So it's looking at that voltage potential difference across the diode. Okay, so it's going to go ahead and it's going to start to vary this power supply. It doesn't care what that voltage of that power supply is. What it's looking for is the voltage across the diode to be equal to 0.1 volts. And so it's going to just start to slowly increase that power supply. And then once it sees that there's a 0.1 volt across that diode, it's going to stop adjusting that variable power supply. Then what it's going to do is then once it gets to that 0.1 volt across the diode, then it's going to take a look and see what the voltage is across that resistor is. And it's going to take that voltage of that resistor, take that measurement, then it's going to use its formula. It's going to take VR divided by R and calculate out the current going across our sense resistor. And once it knows what that current of that sense resistor is, then it's going to put it in there and replace it with the current of the diode. And then it's going to know what that current of that diode is. And then it's just going to plot that little spot. So you can see on our diode characteristics curve that even at, here's 0.7, so we're at 0.1. So it's this little spot right here, this is at our 0.1 volts. And what is our current at 0.1 volts? What is it showing that we have for current at our 0.1 volts? So remember, here's 0, right? The center of my vector is at 0. That's 0 volts, 0 amps. So what is my current going across that sense resistor there? If I have a dot right on that line right there. 0. 0. Okay? Because remember that this diode is going to act like an open until it reaches, for the ideal theoretical number that we use is 0.7. So that diode is going to act like an open until it gets to that 0.7 volts. Nothing's going to happen to that diode. That diode is just going to act like an open until it exceeds that 0.7 volts. So it's just going to keep on doing that. It's just going to do these little steps. Then it's going to go to 0.2. Just the variable power supply. Gets 0.2 volts across the diode. It stops. It measures the voltage across the sense resistor. Calculates out the formula. And then it put the dot on the graph. And so then at 0.2, then we're still at, it's going to be at 0 amps. And it's going to go through all those steps, and then eventually it's going to get to this 0.7 volts. And then it's going to stop. It's going to measure the sense resistor, calculate out the current, and then right at this point here, at that 0.7, then this is going to be right where it's going to start to increase. Okay, so at exactly on our ideal model, at 0.7 volts, so if I'm measuring 0.7 volts across my diode, I'm just ready about to start to turn that diode on. And my variable power supply is going to be, right now, my variable power supply, it doesn't care what that variable power supply is, but right now what that variable power supply is at 0.7 volts also. Might be just, so we might just, depending on where the, in the practical sense of it, this diode is already probably starting to turn on. There's going to be a little bit of curve on there, so let's take a look at it. They don't have a real good one, but drawing up here. So our labels here, this IF, that stands for our forward current. IR stands for our reverse current, our reverse voltage, and then our forward voltage. So what's going to actually happen, what we're going to see on ours is that we're starting out at 0, we're starting to increase, and we're getting closer to that 0.7. And what's going to happen is that the curve is actually going to start to curve in. Once if we zoomed in on this little area here, or didn't do the practical diode characteristics curve, what we're actually going to see is that diode is going to really start to turn on. There isn't much change from 0.6 to 0.7. The current change hasn't changed much. There isn't much change in that. But the current is starting to flow through that diode. and it's going to sense that going across this resistor, and it's going to start sensing that there's some current going through there. Even though that my power supply is pretty close to equaling to the voltage going across my diode, that current is starting to flow through there. It's a very small amount. There isn't much voltage drop across that resistor, but there is that little bit of current going through there. Then as it gets, so now we're kind of, you know, we're kind of sitting somewhere right about here. We're at our 0.7 volts right here. The diode is just starting to allow current to go through there. It's turned on. The current is starting to flow through there. And then it's going to, my variable power supply then is going to measure that, get the current, and then it's going to do the next step. And then this time, what it's going to do is it's going to increase my variable power supply by another 1/10 of a volt. And it's just going to keep on increasing that by 1/10 of a volt. So now we're at our 0.8 volts on our variable power supply. The diode is always just going to drop that 0.7 volts, right? That always is, you know, once we hit that, once that diode starts to conduct, it's only going to drop to 0.7 volts. Even though my variable power supply is going to keep on increasing, my voltage across my diode is going to kind of stop at that 0.7 volts. So now at this point then, now we're really starting to conduct that diode. We've got more of a source voltage than what is our voltage drop across our diode is going to be. Then that remainder of that voltage then is going to go across that sense resistor. And then at that point, this is going to drop the remaining amount. So if it's at 0.8 volts, and my diode's at 0.7 volts, it's going to drop the remainder of the 0.1 volts. Now if I take that 0.1 volts divided by my 10 ohms, and then I calculate out what my current of my diode is. Now any slight change on here, any slight change on my variable power supply, since I'm already conducting, the diode turned on, any slight change now as I start to increase my voltage of my variable power supply, my current is really going to start to shoot up. And this thing is going to go to 0.9 volts, and it's going to go to 1 volt, 2 volts, and it's just going to keep on stepping up that voltage. Once it gets up to 2 volts then, my diode is still going to drop to 0.7. My sense resistor is going to drop the remainder amount of voltage is 1.3 volts. And now you can see that now my current is really going to start to shoot up at a very rapid rate. Okay, so that's all we're doing. We're just monitoring the voltage across the diode. We're sampling it, looking at the voltage of the diode, looking at the voltage of the sense resistor to calculate out what the current's going to be, and it's just going to keep on doing those steps in those incremental steps there. And then what we're going to see is that we're going to see this curve here. We're going to see that it's actually going to start to conduct even a little bit before the 0.7. But at the 0.7, it's going to be right about there, right before it really starts, that line really becomes linear. It's right at that point there. That's kind of considered like our knee current. That's kind of our, where we're really kind of considering that diode at that point is really actually like a closed switch, just like they're showing here. Just remember that diode is either open or closed. Okay. So we're going to hook up the circuit, and then we're going to see what our diode characteristics curve looks like for our particular diode. And each diode is going to be probably slightly different. They're pretty accurate. They're all pretty close, but they all can be slightly different. Okay, so that gives us our forward biasing. Okay, then what we're going to also do then is that we're going to reset it up, or we don't have to reset it up, but But the MyDAC will set it up. And it's going to, then what it's going to do is it's going to flip the power supply around. Now I'm going to be more negative on this side. This is going to give me my my reverse biasing situation. And it's going to do the same thing. It's going to sense the voltage going across that voltage going across the diode. Look at the sense resistor and calculate out the current. Well, we know that if we circle our active component and we put in our polarities in there, if we drew our current paths in there, we know that we're going to be always reverse biased. So is that diode ever going to conduct?
No.
No, it's never going to conduct. But it's going to still go through the same process. It's going to just start incrementing it into 0.1 volt steps or whatever we tell it, how many steps you want it. It's going to start to increment those steps. And so if that diode never conducts it, it's always going to act like a what?
Open.
As an open. And so it's always just going to be equal to whatever the voltage source is. So then the voltage across the diode is going to go to 0.1 volts, 0.2 volts. Then it's going to start, getting up into the larger voltages. It's going to go 1 volt, 2 volts. So at that point, my power, that 2 volts, my variable power supply is set at 2 volts. The voltage across the diode is at 2 volts. Means there's nothing left across my sense resistor, so there's no current going through there. And so then what happens is that now it's going to monitor it. It's going to know that that polarity across that diode is negative, and it's going to just start drawing a line there. So now we're at 2 volts. No current, voltage across the diode is 2 volts, and that just keeps on going. So what's going to keep, if we had a big enough power supply though, and depending on the rating of our diode, and when we get into Zeners, we're going to look at the data sheets and stuff like that. But what's going to happen, depending on our specifications on our diode, if I could, and I could just keep on increasing that voltage to a certain amount, what's going to happen? So we'll just say, for example, on the 914, I think it's, if I'm not mistaken, I think it's about 50 volts. All of a sudden, I get my power supply up to 50 volts. Then what's going to happen is that I'm going to go and get into a reverse breakdown. And what's going to happen is that diode is actually going to start to short out. It's going to start to burn through that semiconductor. It's going to start getting current flowing through there, and then once that current starts to flow through there, the power of that diode starts to increase, and it starts to conduct. And so then all of a sudden my reverse current will all of a sudden start to drop down. This is in a failure mode. That's a failed diode. That's a failure on a regular diode, not on a Zener or anything like that, but on the type of this 914 diode that we're going to start out with, just the regular single diode. That's a failure. That thing has gone into the reverse breakdown at that point. So if we could run it from the whole span of the thing, we go from 0.7 volts, that's the maximum amount of forward voltage that we could ever get across the diode, all the way down into our reverse breakdown, which is, I think, on these diodes is about 50 volts, and then it's gonna fail and then start drawing current again. But we won't see this unless we set up a destructive lab test for it to see what really actually happens.
Okay.
They're not as exciting as a capacitor, but.
Dang.
Alright. Alright, so does that kind of all make sense there? Okay, so we have this analog output that's setting up our voltage, and then when we're looking at our analog inputs, those are just inputs. They're just, all they are is just like taking your, taking your the two leads of your, if I had this hooked up to if I had my two leads of my voltmeter, that's all I'm doing. It's just a voltmeter going into a data acquisition card. It's just measuring the voltage. It's like me just putting in, my positive 0 is my red lead, and my negative 0 is my black lead. And if I were to put that across there, if I was in a reverse biasing like we are right now, if I put my voltmeter across there, I'd measure the same thing that data acquisition is going to be doing. It's going to be measuring that negative 2 volts or whatever we are, because we know that we're going to be more negative on this side of the diode than we are on this side. And if I have my red lead on the more negative side, and my black lead on a more positive side, I'm going to get a negative number. I'm going to measure a negative 2 volts. So it's just like me taking a voltmeter and doing the same thing. The only thing is that I can capture that data, and then I can use that data to plot out charts and graphs and stuff like that. And we just call these sense wires. But basically all it is just a voltmeter. That's all that is. Alright, so right before we do that then when we start hooking these hooking our diodes up into our circuit, then we need to know how we need to identify where that cathode is. We need to know what side of that lead is my cathode, because it's going to be only one side of the lead is going to have the cathode side, and the other side is going to be the anode side. And sometimes those diodes are hard to see, or especially on the light emitting diode, we have a hard time seeing which one is the cathode and which one's the anode. So on a typical, the actual component itself is going to look like this, and then there's going to be a band on here. The one with the band is our cathode side, and this is going to be the other side is going to be our anode side. And if I were to, so it's kind of, so our symbol, our schematic symbol, looks like that. That's what our schematic symbol looks like, but this is what our actual component's going to look like. Well, if we can't see where that black line is, sometimes it's hard, especially on those glass diodes. I think the ones that you got, the 914s are your glass, you have the glass diodes, right? Yep. Otherwise, sometimes the 914s can come in a black casings and stuff. It really doesn't matter. The casing that you're looking at isn't part of the diode itself. The material is inside that casing. But sometimes it's hard to see that black line. So what we can do, since my voltmeter, or since my, not my voltmeter, but my ohm meter actually has an internal power supply on itself, and that's how when we're measuring a resistor and stuff, all we're doing is we're really sending a voltage across that resistor. Then it's calculating out what that current is going across that resistor, and since the voltmeter knows how much voltage it has, and then it watches what the current is, then it can calculate out what the resistor value is. So it just takes the voltage of the ohm meter and divides it by the current of whatever it measured across that resistor, and then it calculates out. And so it would measure out a certain voltage and a certain current, and it would calculate out that it's 10 ohms. So it's kind of the same thing here with when I'm doing a diode check, I'm kind of doing the same thing. All I'm doing is I'm putting my ohm meter across it. It's going to send a voltage across it. And that voltage is typically, on most diodes or most ohm meters, there's enough current to actually overcome that 0.7 volts voltage potential barrier there. So there's enough voltage in there to get that diode to start to conduct. And if that diode starts to conduct, it acts like a what? Open or a short? Short. A short. So my resistance is going to be, so I'm going to start to conduct, and I'm going to start seeing some resistance across there. depending on how hard your, how big of a power supply you have in your ohm meter, because it all varies from power supplies to power supplies, from data acquisitions to whatever, it's gonna depend on how much resistance it's gonna measure. If I have an ohm meter that has a little bigger power supply than another one, you know, so maybe one ohm meter might have like 1.5 volts going across the lead, another ohm meter might have 3 volts. So if I hook up my ohm meter that only has 1.5 volts for a power supply in it, it's going to start to conduct that diode, but it's not going to conduct it very hard, and so the resistance is going to be a little bit higher, or I'm sorry, a little bit lower than if I were to take my other ohm meter that had a 3 volt power supply, and I put it across there. It's going to conduct that diode a little bit harder, and so that resistance of that diode is going to be a little bit less. So it's going to vary from ohm meter to ohm meter what that actual resistance is. Because remember, this resistance in here is all going to be based on how much current it is. How much voltage am I going to push onto it? Then that current is going to increase, and as I increase that current going through that diode, my resistance of that diode starts to drop. So once I identify it and I do this, and it says, yep, I'm starting to measure some resistance, then I know that I'm probably in a forward biasing state. So then I know that my red lead that's on there is going to be my anode, my black lead is going to be my cathode, and then I can go ahead and put that diode in that circuit. But you always want to double check it twice. You want to flip your leads around just to make sure that that diode isn't shorted out. So you're going to flip your leads around, put your black lead on the anode side, put your red lead on the cathode side, and that diode should act like an open and should measure what for resistance?
Infinite.
Infinite. Okay? So that's how we double check our diodes. First we can double check our diodes, make sure that they're good, but then at the same time we can also make sure that we know which side is the cathode side and which one's the anode side. So let me bring up my LiDAC here. I'll bring up the DMM, and we're gonna do the ohm meter test on it first. So I'm going to set my ohm meter on. I'm going to set my ohm meter on ohms. Grab my diode here. And I can see my black line on there, so I'm going to put my ohm meter on the black line, which is, I'm assuming is going to be my cathode, and then my red lead on my anode. And I'm going to switch this to the auto range. Hopefully I can. Might not be able to make it conduct.
Not working.
No, it might not. This one might not have enough voltage to.
Not working.
Nope. So the MIDAC doesn't actually have enough voltage to overcome that voltage potential.
So you gotta use them.
So there's another. So sometimes you gotta watch out which range you're on. So sometimes you want to specify the range. Sometimes, because we know that if sometimes they have to go. If you're gonna go to the highest range, because it's gonna probably have the most amount of resistance with very little bit of current. So we want to make sure that we're in the right range. But it's still saying that it's over. So that means that it still sees it as more than 20 mega ohms, which is still acting like an open. So if it doesn't work with your ohm meter, they actually do have an actual diode checker. That gives us enough voltage and enough current to verify it. So if we switch this over to the diode checker, now you can see that I'm getting a reading, and it's giving me in voltage. This time it's giving me in voltage. So that's going to be the actual approximation of when that diode is going to start to conduct. So at 0.637 volts on mine is when that thing is going to start to conduct and start drawing current. Then if I, so that one is, so that one's going to actually identify an approximation of when that diode is actually going to turn on. Then if I flip my leads around and put my black lead on my anode and my red lead on my cathode, then you can see that it's always just going to say that it's an open. Okay? So typically, if it doesn't have, now like our voltmeters in our classroom and stuff, they'd have enough voltage to overcome the forward biasing of that resistor, and it would show us what the resistance of it would be for that certain amount of current that we're putting through it. And it would show us as the resistance and stuff. Most ohm meters now, or digital multimeters, have the diode checker on there. So you always want to double check your diodes before you put them into your circuit. Make sure that they're not shorted out and everything's working good. You'd also know once you got your diode characteristics curve going, that either whether if you had it in backwards or if you had it in, or if you had actually a bad diode. Alright. Alright, so now let's go ahead and we'll try we'll run our VI, our diode characteristics curve. So I gave you a folder with that was called curve tracers. And inside that one with the curve tracers was where I had to, I gave you a bunch of them. We're going to use them. The one that we're going to start out with is the NI 2-wire curve tracer. That's the best one. This other diode curve tracer, that one's okay, but it doesn't, it's good for checking your diodes and stuff like that, but it doesn't work as well as the NI one. This is from, these other ones are from another professor that had developed these on his own and stuff like that, and we're going to use those for the transistors and the FETs, and his works really good for that. But for the 2-wire one, the NI one works. The one that comes with NI is the best one. So what you're going to do is if you haven't done it already, what you can do is you can copy all those, highlight them all, take them, copy them, come back down to your MyDAC launcher, go to My Files, and now they actually have a link on that. Since they upgraded it to the 4.5, now there's actually a link that you can see I already have mine in there. But yours just might say Launch My Files folder. If you click on that, it'll open up that file where those get stored at, and then you can just paste them into that directory. So then when you do that, then you have all these extra files that you can use. Those your custom VIs that you can use with the MyDAC. So get all those curve tracers put in under the My Files, and we'll use that. Anyone having problems with doing that?
How do we get there?
It's on the Google Drive.
If you're on Facebook, then go to the Nokitech Friends of Facebook. I think try going to Friends of Nokitech. You have to log. I think you have to log in no matter what, right? Yeah, you have to. Yeah. All right. Let me get a. I'll put it on a flash drive here and.
Kurt, can you just send him a link by email?
But yeah, I think it'd be easier. Otherwise, I'd get all their email addresses.
Oh, that's true.
I'll just put it on my, couple of my flash drives here.
When I go into the MyVac thing, it's.
I'm still curious, this little thing that they gave us with all our stuff, the little group thing, is that what it's meant for, or what?
Yes, it is.
It's like,